doesn't matter what mode I'm in. We planned on getting to these calculation questions yesterday. Maybe I was too busy shouting at you or I ran over time. But let's just quickly finish this wavelength down here. Now, there is a poster on the second page that has all of the metric prefixes. Down here, there is a little symbol, micro. That means 10 to the negative 6. 1 micrometer is 1,000 nanometers. That lowercase n means 10 to the negative 9. We measure the wavelengths of light. Come in, Sam. Find a spot somewhere. We say nanometers, but really it's down here we have 380 nanometers. 5, 6, 7, about 750 nanometers. So it's two different ways of saying it. You could say 7.5 times 10 to the negative 7, or you could go 750 nanometers. This is a good tie-in. We've also got another one here, capital M for mega. What I'm getting at, gentlemen, is we're dealing with really, really high frequencies and really, really short wavelengths. So you need to know those metric prefixes. Hugo, you need to know scientific notation. We're going to be doing some calculations in today's class, and then you're going to be doing some work. You need to be proficient with your calculator. So, if we just went back to the light bulb, the light bulb's at a certain temperature. This is the spectrum. These are all the different wavelengths that are being emitted. Some are in the infrared. This region here, longer wavelengths, infrared. Yes, TJ?
Is there any that have most of it in the purple blue?
Well, if we had a light bulb that was at 3,700 Kelvin, so it's about 3,400 degrees Celsius, it's pumping out a whole lot of infrared. You could hold it near to your face and go, yes, I can feel the heat. It's pumping out lots of red and then a little bit less OIG-BIV, all right? So all of that's going to your eyeballs. You don't see the green photons, you don't see the red photons, you see a mixture of colours. So you see a bright yellow colour, okay? Now, by the time we get up to the sun, all right, that's what the sun is pumping out. So we get the infrared, we get more green and blue, and a little bit less of the ROI and a little bit less of the BIV, okay? You throw that at your eyeballs, we would see a mixture of white light, all right? So anything that's that temperature, we would say it burns white hot. If you got metal to 5,000 degrees, it'd be liquid and it would be glowing white. You hold it near to your face, you would feel the heat, you would see the light. This region here is ultraviolet. That section, that's the ionizing section. So you would eventually get a sunburn, okay? If you held molten metal to your face, the ultraviolet would be damaging your skin, all right? You get sunburn.
Is that like when you're welding an actual light?
That's it. So the welder's mask is obviously to protect your eyes, but it's also to stop you getting burnt. If you just welded with normal sunnies, you sort of squint a little bit when you're melting metal, you'll end up with a massive burn on your face. And you have like the trading tan where you can see their glasses. So that all of this comes down to the earth. Some of it gets absorbed by the atmosphere, but some gets through. All right, so that's why we have the number on the gym currently says 2. That's the UV index. It's a measure of how much UV light is getting down to the Earth's surface. Now, when it's a low index, it means most of it's been absorbed. Well, there's 2 reasons. Obviously, the sun is low in the sky and it's winter. There's lots more moisture in the air. So in the atmosphere, those gases are going to absorb a lot of the UV. In the middle of summer, 12 o'clock, so the sun's directly overhead, there's no cloud, the UV index might be extreme. It might be up to 10 or 11 or 13. That's saying that there's a lot of these UV ionizing wavelengths. They're going to damage your skin. And so if it's in that range, then you've got to slip, slop, slap, sunscreen and hat and all that jazz. Okay? So, could we please get to the table on page 2, the blue table? We're just going to highlight some of the important ones that we want to use in this. Now, guys, your test, Hugo and Jack. This will be in the test on Wednesday. We want the 10 to the 6 is mega. So, where's my... Oh, come on now. 10 to the 6 is mega. That's capital M. 10 to the 3 is kilo. Marcus, knock it off. So that's your lowercase k. You've got capital G is giga. All right, so a gigabyte is a billion bytes. We can go to the lower ones. 1 millionth is micro, and that's the Greek character mu. And then 1 billionth is nano. All right. So a nanometer is 1 billionth of a meter. If I took this white piece of plastic and sliced it into 1 billion increments, they would have a length of a nanometer. If I added 700 of those, 700 nanometers, 700 billionth of a meter, electromagnetic radiation of that wavelength into your eyeballs, you would see that as red light. Okay? So, in year 11 and 12, Hugo, physics students usually use the orders of 3. So you've got kilo, mega, giga, and then tera, a terabyte. And then going the other way, you've got milli. Oh, I forgot milli. A millimeter is 1,000th of a meter. We can see a millimeter. They're the little ones on your ruler. All right? So that little millimeter is 1,000th of a meter. It's 10 to the negative 3. It's 0.000. Too many zeros. You know, there's different ways to write it. Could we now get to... You need to obviously know these regions of the electromagnetic spectrum and possible uses or causes. Oh, I'll tell you about this story about the gamma ray. Did I get angry at you guys yesterday and just went to this table? Yeah, I was going to tell you a story.
But Isaac Newton.
Yeah, that's right, but not now. My friend, who I've known since year 8, I still know him. When we were at university, you know, early 20s, he had a girlfriend. She turned out to be crazy, so he dodged that bullet. But he went to the Philippines and he bought this little wooden drum. Right? And he's like, this is a perfect present for my girlfriend. This is a true story, I'm not lying. Perfect present, little wooden ornate drum, and it had the little the hide that had been stretched over so you could tap the drum, and it was roped, it was tightened to the drum, and it had these little ornate beads going through the ropes. He's like, yep, he bought it like $20, $50, whatever it was. He brought it back to Perth. They landed in customs, and Perth Customs took one look at that and said, yeah, nah, that's not coming into Australia. That's got wood. It's made of cowhide. It's got flesh in it. It's got nuts. It's just, no, we're not bringing that into our unique flora and fauna. If there's anything nasty in that drum, it could do nasty things to our agriculture. So Customs said, look, he declared it. You know, that's why when you come through Customs, you've got a piece of paper, you can declare things. If you're honest, you go, I can declare I've got this drum, and you know, they'll have a look at it. If you think you can get away with it, you don't declare things, but then if you're caught, then you can get fined and you can get in trouble. So he declared it. The Customs said, all right, you got 2 options. We throw this thing into a massive furnace and turn it into ash, and away you go, no more drum. Or, for the extra $150, we can bombard this drum with gamma rays. They irradiate it with ionizing radiation. So they sit it in this machine and they blast it with gamma rays. And what that does is it ionizes all of the molecules in that drum, all the wood, all the skin, all the bacteria and the nuts and the little weevils and the moths that are hiding in, kills them all. Right? Still a drum, it doesn't crumble into ash, it's still a drum, it still works. He did that. He paid the extra $150 and he came back 2 weeks later. He drove to the airport and picked up this drum, his birthday present for his girlfriend, turned it into a $200 drum, and then they broke up anyway because she was crazy. So anyway, that was an expensive story, but that's an application of gamma rays. Obviously, here's the thing. There's a lot of nasty stuff floating around in space. There's stuff called cosmic background radiation. There are X-rays and gamma rays and charged particles whizzing through space. We are protected by our atmosphere. So any of the nasty stuff hits our atmosphere, pretty much gets absorbed. Okay? So we're quite fortunate that we have an atmosphere. If we didn't have the 40,000 metres of gas above us, if we walked outside, you would pretty much get an instant sunburn, and you would pretty much fall over after a couple of minutes, and you would pretty much be cooking like a chicken on the ground. You would just be blasted with all of this high energy radiation. Okay, so planets that don't have an atmosphere, this EMR is going to be doing damage. And that's one of the main problems of us. If we want to go to Mars and terraform Mars and turn it into a new Earth, that's the problem. How are we going to deal with all of this stuff that's going to occur? Lots of interesting stories, but let's get on to the mathematics of the stuff. Could you please go to page 6? Recall I said we can use the wave equation V equals F lambda, but for all EMR, they all travel at the speed of light. So we're going to say C equals F lambda. You can throw him into a good old triangle. All right. You can rearrange that equation to solve for your unknowns. Okay. So, page 6. Page 6. Okay. So if you're rearranging for F, it's going to be C divided by wavelength. And if you're rearranging for wavelength, it's going to be C divided by F. Okay. And you will need to do what I said when we did motion. You highlight the things that you have in the question, you highlight the unknown, and you go about solving. But I'm going to throw in a couple of tricky bits. For example, Triple J broadcasts at 99.3 megahertz. That's 10 to the 6. So could we write over here, frequency equals 99.3 times 10 to the 6. William, you're not putting a capital M in your calculator. You're going to put times 10 to the power of 6 in your calculator. Okay? So, we're not even told the wave speed, but we know that radio travels at the speed of light. So that's 3 times 10 to the 8. All right? We're going to use our equation lambda equals C over F. Now, here's where you're all going to race to your calculators, and this button is your friend. Okay? You're going to use the fraction button. All right? It eliminates the chances of you making mistakes. All right? BIMDAS and all that. If you forget one bracket and then you stuff up the equation. So, in your calculator, you're going to use that, and you're going to throw him at the top, and then you're going to throw him at the bottom. 99.3, try that again. And if somebody wouldn't mind telling me it's 300 on 99, it's going to be 3 point something.
3.02.
Okay. So, the funny thing is, gentlemen, that waves of this wavelength are racing into this classroom at the speed of light, and they're bouncing around, and we don't know about it. Because our eyes can only detect wavelengths of 10 to the negative 7, and our skin can only really detect infrared, which is about 10 to the negative 3. If there was a microwave, then we would all be, it burns, but we don't put microwaves into the classroom.
Wait, we wouldn't feel the microwaves burning us.
Oh yeah, it would cause the water in your skin to start to heat up.
There's no heat.
So we don't ever put people in microwave ovens, and we don't ever blast microwaves around where people could walk around. What was I getting at? It's in this room right now. 99.3 Triple J is racing through this room right now, but we don't see it, hear it, feel it. But you take an aerial and you tune in your aerial to 99.3, and you can make your electrons in that aerial jiggle up and down. Right? So have a think about it. All the radio stations, all the TV stations are whizzing through this room right now. If I wheeled in a TV, I'd be able to prove it. Turn on the TV, it gets the signal. Yes?
You know why the amp, is it like, it's more prone to like interruptions and stuff?
Yeah. because the electric field of power lines stuffs up the wave. So if you're ever listening to AM radio and you drive under high voltage power lines, sometimes you get that, it zooms out. Frequency modulation is a better way of transmitting signal. How did you know that? You're having a Google. Good. I like that. A Wi-Fi router. Oh, gentlemen, we have one of them. Look at the almighty box that we can prey upon to make sure that we get internet. Here he is. All right. He's pumping out waves. Inside that little box up there would be a little aerial, and in that aerial are electrons, Max and Jack. They are oscillating backwards and forwards 2.4 billion times per second. That's gigahertz. Could you recall giga is 10 to the 9? So now our frequency is a little bit faster than the radio frequency. It's about 1,000 times faster, or 20 times faster. 2.4 times 10 to the 9. It's the same wave that travels at 3 by 10 to the 8. And so we're going to do wavelength equals. And can everyone, if you haven't already, get your calculators out. Use that fraction button. Yes, TJ?
So when you're like the end of the range for like, say, your radio.
Yep.
What makes it, so is it just because the waves are going too big?
Yep, so essentially in Australia, you are allowed to transmit in a certain band, right? So you've got a bandwidth. So in your FM radios can go. That's why your your car radio starts at 88 and finishes at 106. That's the band that radio stations are allowed to operate in. It's the same with TV.
Why is that too regulated?
Why
is that regulated?
Well, because it's a commercial industry. People sell bands on that that band width. Channel 7 is only allowed to operate between, I'm making this number up, but it might be 98 to 101. So in that band, they can put 7, 7 mate, 7 HD, 7 Go, 7 4, all the bloody 7 channels. And then the next band across, Channel 9 has purchased the rights to use that. So there's lots of interesting stories about selling airwave. What do you call it? Selling airwaves. Yeah, you're paying to send out waves in that frequency, right? And so if you've ever tuned your TV, you go into auto tuning, and some TVs will show you as it's going through all the frequencies, boom, 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 all the TVs pop up, right? So they're broadcasting in those regions. Yes. These are really good questions, but could somebody tell me what this wavelength was? 125, cool.
What's the difference between FM and AM and DAB?
Ollie will tell you because he Googled it. It's a different way of putting information onto the wave. You can put it on the amplitude or you can put it on the frequency. That's as much as you need to know. In fact, you don't need to know it in year 10 minutes. Hold on. Gentlemen, listen please. William, boys, this little box. It's jiggling backwards and forwards in there, and the ripples are coming through. And the space between the crests of these waves racing through this room at the speed of light are 12.5 centimetres apart. Right? They come racing down and they slosh around your head. Long waves can basically go around objects. So right now, William is an object in the way of Rishi's laptop. Right? So if it was visible light, very short wavelength, William would be quite a large object, and the short wavelength, it wouldn't get around. There would be a shadow. So you wouldn't be able to see the router. If you were in William's shadow, you wouldn't be able to see. But the longer waves of the Wi-Fi are bending around William and continue travelling. So that's why Rishi could place his laptop behind William. You're going to get the signal, right? It bends around. It's the same with the door. If I open the door, it diffracts through that big gap and it spreads out. The year 11s and 12s are learning about wave behaviour. There's a relationship between the size of the wave and the object that it can get around. Basically, if the wavelength is about the same size as the object, it will be able to get around that object. So if you're a radio wave that's 3 meters, you should be able to bend around a building. That's why, let's say there's a radio tower off on the horizon that's broadcasting out Triple J, and you go and stand behind a house. Well, you can still get the reception, all right? You can still get the radio signal because it's bending around the object. Your Wi-Fi, however, that might not be able to get through. All right, so your Wi-Fi, the smaller the wave, the more likely it's going to get sort of trapped. Okay, here's a new one, a green laser pointer. 512 nano, that's 10 to the negative 9. So wavelength equals 512 by 10 to the negative 9. And now we want the frequency. So there's a little crystal inside a green laser pointer that oscillates backwards and electric charges backwards and forwards, and it sends out photons. We want the frequency. What's the equation? It's C on lambda. We're going to take a big number and we're going to divide it by a small number. And your knowledge of maths is you're going to get a really big number. Could somebody tell me what it was? 10 to the 14?
5.86 times 10 to the 18.
Whoa.
Oh, that's hertz. Oops.
Hertz, yeah, so that's our, remember that is our symbol for frequency. Frequency is in hertz.
Oh, that would be like a blue light.
All right, next page, we'll do 2 more examples and then you're going to do the homework questions in that booklet. Let's go over the page. Let's just say that violet light has a minimum of 380 nanometers. All right, so remember we're combining the little n, means that. And let's go that red caps out at 750 nanometers. And in the previous question, we looked at about 512, 532, whatever it was. You're going to use the same equation. You're going to use that. All right, and we're just going to change the wavelength. Could you get over the page, get your calculators out, get those fraction buttons pumping?
Wait, what is it?
Okay.
What was the other number?
T.
380 and 750.
Oh, 1 over F.
And I'm pretty sure there's going to be a question like this. You've got to use the wave equation and you've got to use scientific notation. All right. William or Jason or Ted or someone who has
Done it.
worked these out.
Oh, so the one on the left is 3.92 times 10 to the 18 hertz.
Cool.
And the one on the right is 7.89 times 10 to the 18 hertz.
Thank you very much. Okay. So this is why, did you guys do scientific notation in maths year 9, year 10? Yep. This is a scientific notation helps us deal with really, really big numbers and really, really small numbers, which is what we are dealing with right now. All right. 10 to the 18. All right. Last question. Let's do frequency of this bad boy. So this is going to be smaller than visible light. We're going to be like ultraviolet or something, but let's figure it out. 3 times 10 to the 8 over 1 times 10 to the negative 11. That's 3 on 1, add 11 to 8, you'll get 10 to the 19 hertz. Now, let's race back to our posters. You can use either the wavelength or the frequency. Go back to the posters on there's, I think, 2 posters you can use. Go to frequency at 10 to the positive 19 or go to wavelength at 10 to the negative 11. You should be able to find the name. Wavelength 10 to the negative 11 or frequency 10 to the positive 19. What are we at? X-rays? or gamma rays? Do we have another poster? Let's look at this one. I'm going to look at the poster on page 2. It's X-rays, yeah, 10 to the negative 11. Or frequency 10 to the 19. Ooh, yeah, we're just in the X-ray region. I would say X-ray. Okay? And while you're working, I'm going to bring up the inside page of the test, and you can see the equations that you will have at your disposal. You might have to do something similar. You might have to look at a poster and figure out the regions. I don't know. I can't remember. I haven't looked at the test in a couple of weeks. The period of the wave, that's t. Well, we know that t equals 1 on f. So we're going to take that frequency and go 1 over. That's going to be 1/3 by 10 to the positive 19. That's 3.33 by 10 to the 18 seconds. Okay? All right. That's me done talking. Could I ask you to find the homework? Homework sheet 14, please. Get going. And I'm going to ask you to get your homework out, which was homework sheet 12.